So imagine you are opening a box from the dental lab and you're expecting a perfectly polished denture, but instead you are holding something that looks entirely like Swiss cheese.
Oh, yeah. That is definitely a sinking feeling. And if you are prepping for your ADC OSCE exam, well, case 12 from Odell's clinical problem solving in dentistry is basically your worst nightmare.
Right, exactly.
Good.
So today we are doing a deep dive to crack exactly why this happens, specifically in both acrylic and cobalt-chromium dentures. Let's unpack the first half of this case.
Sounds good. So we have a heat-processed polymethylmethacrylate denture, PMMA,
Yeah.
but in the thicker areas of the acrylic, like right inside the teeth, there is this horseshoe-shaped cluster of small, perfectly round holes.
And what exactly are we looking at there? I mean, what is the differential diagnosis?
Well, to diagnose this, you really have to rule out a couple of other things first, like you might see contraction porosity, which is where holes are spread everywhere.
Oh, because the lab didn't pack enough material into the flask.
Exactly that. Or they just didn't use enough pressure. Or, alternatively, you could see granular porosity. That makes thin sections look weirdly white and frosty, usually because the polymer to monomer mixing ratio is just off.
But neither of those actually match our specific horseshoe cluster in the thick areas, right?
Right. Now, our culprit here is gaseous porosity. The monomer literally vaporized. You see, a methylmethacrylate has a boiling point of 100.3 degrees Celsius.
Wait, 100.3.
Yeah, so if it gets hotter than that during processing, the liquid monomer just turns to gas, and that leaves those sharply defined round holes behind.
Okay, but here's where I'm a little confused. If the lab knows the exact boiling point is 100.3 degrees, I mean, can't they just set a thermostat on the water bath to stay below that?
See, that is the trap. The polymerization reaction is actually exothermic, meaning it generates its own heat.
Oh, wow.
Yeah, so even if the water bath is safely sitting at, say, 70 degrees, the thickest parts of the acrylic are generating all this internal heat that pushes the core way past that boiling point.
Ah, I get it. So it is less like baking a cake in an oven and more like, I don't know, pouring a really thick slab of concrete or mixing two-part epoxy.
That is a perfect analogy, yeah.
The chemical reaction creates so much heat that if it is too thick, it literally cooks itself from the inside out. So how do you actually stop that from happening?
Well, it takes two steps. First, trial packing the dough under pressure. That actually raises the boiling point of the monomer.
Okay, that makes sense. And the second step?
Second, you just process it low and slow, say 72 degrees Celsius for about 16 hours. That gives the internal heat plenty of time to safely dissipate.
So heat management completely solves the acrylic mystery. But let's look at the second half of case 12. We have a cobalt-chromium metal framework presenting with the exact same bubbly perforated defect.
Right, and obviously monomer boiling isn't happening in solid metal.
Exactly. So what is the mechanism here?
Oh, it is a total chemical disaster.
Yeah.
With cochlear castings, those holes mean someone used a gypsum-bonded investment instead of a phosphate-bonded one.
Wait, if gypsum creates destructive gas, why is it even sitting in the dental lab to begin with?
Well, because it is perfectly fine for metals with lower melting points.
Like gold-based alloys.
Exactly. But cochlear requires extreme heat to melt. And at that temperature, the gypsum, which is calcium sulfate, breaks down and reacts with the silica refractory.
And that reaction releases gas.
Yes, it releases sulfur trioxide gas. And that gas just, bubbles right through the molten metal.
Wow. So just a simple mix-up, reaching for the wrong bag of powder. Gypsum causes the uniform Swiss cheese effect. But what if the lab tech sees irregular voids instead of round ones? Does that point to a different chemical reaction?
That is a great deduction to make. Irregular voids are usually physical, not chemical. It points to casting shrinkage from turbulent flow.
Turbulent flow meaning the metal is splashing around.
Pretty much. This happens when the sprues, which are the channels feeding the molten metal into the mold, are either too narrow or they're attached in the wrong position. The metal churns and splashes as it flows, leaving jagged gaps.
Got it. And what if the holes are perfectly spherical? That feels like a gas issue again.
Exactly right. Spherical voids usually mean the lab overheated the alloy. At those excessive temperatures, the molten metal actually absorbs gases from the atmosphere.
Oh, and then when it cools.
Right, when it finally cools and solidifies, those trapped gases desperately try to escape, leaving perfect little spherical bubbles behind.
And I imagine if the cast is just short or incomplete, they either didn't use enough casting force or the mold itself was just too cold to let the metal flow completely before hardening.
Precisely. So for your ADC OSCE exam, the big takeaway is that you really have to look deeper than the surface.
Because identical-looking defects, like those small, round holes, have entirely different root causes depending on the material.
Exactly. With acrylic, it is all about physics and heat management. But with cobalt-chromium, it is about chemical compatibility and fluid dynamics.
It really puts things into perspective. I mean, you spend years mastering your chairside clinical skills, right?
Mm.
Perfecting your impressions, getting the margins exactly right.
Honestly, so much time goes into that.
But isn't it wild to consider how much of a patient's ultimate daily comfort relies entirely on an unseen technician simply reading the label on a bag of powder? One wrong scoop, and you are back to serving Swiss cheese.